In this video, I'm going to continue talking about linear vector fields. That is, we've got a differential equation x dot equals ax, and I'm going to tell you a little bit more about eigenvalues and eigenvectors and how they influence the solutions to this kind of differential equation. So recall that an eigenvalue is a number lambda for which there is a non-zero eigenvector v that satisfies AV equals lambda v. So now suppose that we have, suppose lambda is an eigenvalue, and I'm going to just form the matrix, or form the vector x equals e to the lambda t times v. As before, I can do a little bit of checking with this. X of 0 is, well, just 1 times v, which is v. But furthermore, x dot, so derivative with respect to time, is lambda e to the lambda t times v, which means that x dot happens to satisfy x dot equals lambda times x. Now, that means, nope, that's not what I wanted. That means that x dot, well, maybe I should write it like this. X dot equals e to the lambda t times v. Lambda v is AV because A is a matrix and V is an eigenvector of the matrix and lambda is the eigenvalue associated with V. So now if I move my scalar around a little bit, I can rewrite this equation like this and get x dot equals ax. So in the previous video I showed you about matrix exponentials. It turns out that a very similar calculation allows you to conclude that if you have an eigenvector v and its eigenvalue lambda, you can also construct a solution to the differential equation immediately from those two pieces of information. It's also possible to start with all of the eigenvalues and eigenvectors and reconstruct the matrix exponential calculation by essentially stacking together equations of this form, but I'm not going to do that right this minute. The key thing here is that if lambda is greater than 0, and it's a real number, then e to the lambda t times v will grow in the direction of v. If lambda is a real number and less than 0, then e to the lambda tv will shrink in the direction of v. Now suppose that you have suppose that we have two eigenvalue eigenvector pairs. So A times V1 equals lambda 1 V1, and A times V2 equals lambda 2 V2. And I'm going to assume that these are independent solutions, so V1 and V2 are linearly independent. And as long as lambda 1 and lambda 2 are not equal, that has to be the case. Things get a little strange if lambda 1 happens to be equal to lambda 2. We will talk about that later. So that gives two families of solutions to x dot equals ax. And so one solution is e to the lambda 1t times v1, and the second is e to the lambda 2t times v2. Now, if you'll recall, the solutions to an equation like this that's linear in x, so this form, these form a vector space. That means any linear combination of solutions is itself a solution. So there are other solutions, and I'm going to call these, let me give them a different name. How about Z? No, I don't want to call it Z. Let's call these U. I'm probably going to be sorry I called them U, but let's continue. A1 e to the lambda 1t v1 plus A2 e to the lambda 2t v2. So A1 and A2 are scalars. So now I now have a sort of general family of solutions. Now, if A happens to be a 2 by 2 matrix, then this is the general form for all solutions to x dot equals ax. Well, let's continue. Let's continue assuming lambda 1 and lambda 2 are real. Okay, so what happens when lambda 1 and lambda 2 are real? Well, in this case, you're going to get solutions that are made up of a component in the v1 direction added to a component in the v2 direction. And I'm going to suppose that lambda 1 is greater than 0 and that lambda 2 is greater than lambda 1. So what will be happening is that there are solutions that grow along a line parallel to v1 and solutions that grow along a line parallel to v2. And because lambda 2 is greater, they will grow faster in the v2 direction. So faster growth in the v2 direction. That means that solutions will look something like this. No, I've drawn that backwards. No, that was right. They'll grow faster in the v2 direction. The reason that I'm drawing them like this is that this is this is the coordinate plane, and the origin is right here in the middle, and you can also get solutions that sort of point the other way like that by using negative numbers for A1 and A2. So that's the case if they're both positive. This is called an unstable node. Now, if we can do an unstable node, we can, of course, do a stable node. A stable node, again, let me draw in some eigenvectors. There's v1 and v2. There's minus v1 and minus v2. But this time, we're going to suppose that lambda 1 is negative and that lambda 2 is less than lambda 1. So that means that we have rapid decay in the v2 direction. So now solutions are going to look like this. Both parts of the solution will be decaying in the case that lambda 1 and lambda 2 are negative, but the lambda 2 part will decay more quickly because lambda 2 is of greater. You know what, I have been drawing these backwards. Nope, I'm drawing them backwards again. I'm drawing the other kind of backwards. Okay, so that's what the solutions look like. The stable node and the unstable node should look basically the same, just with the trajectories running in reverse. Finally, what happens if you have one positive eigenvalue and one negative eigenvalue? In that case, you have something called a saddle. So let's suppose that lambda 1 is less than 0 and lambda 2 is greater than 0. So then you get decay in the v1 direction, but you'll get growth in the v2 direction. Okay, so what does that look like? Well, you'll get decay in the v1 direction as time goes on, but you'll get growth in the v2 direction. So trajectories will start, the v1 component will shrink, but then the v2 component will grow. And so that's what the saddle looks like. Let me show you these three kinds of fixed points with a numerical calculation. So let me show you this numerical calculation in Mathematica. What you're looking at is something called a stream plot that shows just little bits of solutions to a differential equation. And I've picked out the eigenvectors v1 and v2. And up here, I've set up the eigenvalues so that we can change them around. This is the case. Let me go ahead and start with this case. So this is the case of a stable node, and lambda 1 is minus 1, lambda 2 is minus 2. So you can see also here I've got one solution highlighted So this is an initial condition, and in forward time, the solution converges to 0 like that, and if you were to go backwards, you would back up the solution going that way. Now what you can see is that the eigenvectors sort of control the way the solution swerves. The length of the eigenvector doesn't really matter. You can choose any eigenvector you want, and the solutions in the vector field stay the same, other than for the wobble in the mouse. And all of these, well, the easiest ones to see are that if I set up the eigenvectors to be perpendicular, almost got it. The solutions actually follow power curves, where y is just a power of x. That's an easy calculation to do, but I'll leave it to you to look at that. If I interchange the two eigenvectors, two eigenvalues. If I interchange the two eigenvalues, you can see that the curvature changes. And so this is what I was trying to get right a few minutes ago, to get the curvature right. So in this set of parameters, in this setup, lambda 1 is decaying more rapidly, so you can see that the solution sweeps in like this, and then the v2 direction, it's a little slower. Okay, so what happens if I go up here and, oops, I overshot. Nope. Now I have one positive eigenvector and one eigenvalue and one negative eigenvalue. The positive eigenvalue is associated with this eigenvector v1. The negative eigenvalue is associated with eigenvector v2. And you can see here that, yes, solutions in forward time will swoop in toward the origin and then fly outward following v2. So this is a saddle. And if let me change this. If I change things so that lambda 1 and lambda 2 are both positive, then now you can see solutions flowing away from the origin. This is the unstable node. And because lambda 2 is greater than lambda 1, the solutions swerve like this. Okay, so that is what a node, a saddle, stable and unstable nodes, and what saddles look like. Now, I want to also show you one last thing, which is what if the eigenvalues happen to both be equal? In this case, the solutions follow straight lines. The reason for that is that if the eigenvalues are equal, then what you're seeing is a system where the A matrix is just scaling uniformly in all directions. And in this case, there's no bend at all to the solutions. They just flow away exponentially along a straight line, just parallel. And a way to see that algebraically is that if the eigenvalues are both equal, then as long as I've got two independent eigenvectors, the entire plane spanned by those two eigenvectors consists entirely of other eigenvectors. And so you get these solutions that just flow away from the origin directly. So this is sometimes called a star node, and I can also show you a stable star node by making lambda 1 and lambda 2 both negative. So same basic shape, only now solutions are converging in to the origin.